What I want to talk about now is something called analysis. Now, that word might mean psychoanalysis, but I'm not interested in that. I'm talking about mathematics. Analysis is the mathematics of continuous functions of continuous variables. They're the basis of all the laws of physics today. The problem I have with analysis is I don't believe physics has any continuous variables. So that would mean that the whole of modern physics is at best a very good approximation to what happens with physics. Now, you might say, well, isn't there fantastic evidence, this analysis and analytic functions such as differentials, and which are derivatives and integrals, have, since Newton, who had to invent the calculus, and Leibniz, and in the beginning, who sort of did it for mathematical reasons, has been revolutionary in its application in wide areas of physics. You see, that has to do with some fundamental facts. One is there's these great continuous symmetries which most physicists today, except for me basically, believe is at the very foundation of physics. The great continuous symmetries are things like translation symmetry. The laws of physics are the same in any reference system as long as it moves with unaccelerated and irrotational motion. In other words, if it's moving steadily, the laws of physics within it are the same as for it not moving. If it rotates, then they're different, of course, because of centrifugal force and stuff like that. So that's at all these continuous symmetries, such as rotation symmetry, translation symmetry, time symmetry, etc., are thought of in physics today as the most fundamental thing in physics. I don't think it's fundamental, and I'll explain why. A wonderful mathematician named Emmy Noether, it's spelled Noether, she was a fantastic mathematician who was a student of Hilbert, who was one of the greatest mathematicians of all time. And in Germany, when she studied under Hilbert, she wanted to give lectures. The university said women can't think, so no, can't be done. So Hilbert would schedule a lecture and she would give it. So that was the only way he could do it, because they wouldn't let her be a faculty member. Eventually she migrated to the United States and so on. Before she died, she proved an amazing theorem, which today every physicist knows. It's called Noether's theorem. And here's what Noether's theorem says. It says that for every law of continuous symmetry in physics, there's a corresponding conservation law. Well, let me give you an example. Translation symmetry says the laws of physics are the same in any reference frame that's in continuous irrotational motion that's not accelerating. In other words, if something is moving at 17 miles an hour steadily northeast and a little bit up, okay, in that direction, continuously, then the laws of physics in that region that's moving like that are the same. You can think of it, Einstein used a train or a boat in his examples to sort of illustrate certain points in a similar fashion. But that's just an observation that they are the same. Okay? Now, if my ideas were true, they wouldn't quite be the same, and it might be detectable. Okay, so if I see, because I believe at the bottom there isn't just this continuous space, but there's some discrete space like a checkerboard. And this checkerboard would be very small, but things, you know, each cell would have on this checkerboard, whether it's black or red, doesn't matter, each cell would be in some state. And there's only maybe 3 different states per cell. Okay. And I believe you can model all physics down by a process running at that level on a Cartesian lattice that's a fixed lattice. And this makes most physicists think I'm a crackpot because a fixed lattice is contrary to known physics. Because they can't imagine how you could get the laws of physics we have if underlying it there's a fixed lattice. Well, I think that the reason they can't imagine it is that they don't have a good imagination in terms of one thing. You have to think about computers and what they can do if you want to discover some of these things, because physics sort of rules them out. So my ideas don't make sense if you assume the laws of physics are always what we think they are, down to the nitty-gritty, most microscopic effects. Instead, what I propose is that there's some discrete system like a cellular automaton, and that discrete system is functioning, and we as observers working in physics, as we do with our instruments, make measurements, we're so far above that system that it's just like atoms. We don't normally see the atoms that make up a gear, but the gear works fine in spite of the fact that we can't see the atoms. Okay? So what I'm saying is that there may be things that are much smaller than atoms, and it's states of a discrete space that's fixed. Well, if it's fixed, I have a whole bunch of big problems because I have to answer the big question, where does this obvious to us continuity come from? And why if there's a fixed lattice that has a definite direction in north, south, east, west, say, and up and down, if it's Cartesian, then where is the evidence of that? Well, there isn't any. But I can explain why. Because if my process happens to conserve momentum exactly, even though it's discrete momentum, at a high level, we would have the laws of physics we have because, and we would come up with the same ideas because of Nutter's theorem again, except done backwards. Because Nutter's theorem says that a continuous symmetry generates a law of physics. Okay? What I'm saying is, gee, if we have the law of physics, maybe we get the continuous symmetry. And the law of physics might be discrete, but you still get the apparently continuous symmetry. So it turns out that a discrete underpinning to physics could meet all the requirements of the measurements we've made on the universe so far. In other words, I claim that all the measurements we've made that support the current theories of physics are also in concert with the concept of a discrete underpinning and discrete state, a small number of states per cell in that underpinning. And small number, I mean maybe 3. Okay? So that's...
So give me a conclusion. So in conclusion, just kind of give me one of those, okay?
Okay. The point of my talk, for the most part, has been to convince you, the audience, that you ought to think about the possibility of discrete models at the most microscopic level in physics. Now, I believe that one of the things that will be the most important early result will be a proof that such discrete models can produce all the physics we know and measure today. Okay, that would be a first step in solving the eventual problem or answering the eventual question. Well, if it could model physics, does it model physics? In other words, at the bottom, is there a discrete system or not? I believe that that question is answerable by experiment, but I don't know the experiments yet.